Good morning. My name is Pete Robichaud. I'm with the Forest Service Rocky Mountain Research Station. Today we're going to talk about a rill experiment. This is one of the experiments that you do in erosion research. It can be done in forest environments, rangelands environments, and agricultural environments. One of the standard methods that was used to develop the WEP model, the Water Erosion Prediction Project, and we've of course modified it to work in different types of conditions. One of the advantages of this experiment, it allows you to do a couple of different things. One of them is to do a direct comparison between a particular treatment on the rill erodibility or the rill erosion that would occur. So today we're out in a forest environment. We're on the rim fire. This fire burned in 2013 and it's 2016, so 3 years after the fire. We've been doing this experiment every year. We've done it on areas that were burned and logged, some areas that had skid trails, and then some areas that had some skid trails with an additional treatment of ripping up the skid trails or subsoiling to reduce that compaction and increase infiltration. So the goal today with this little video is to walk you through the steps to set up a rill experiment. So I'm going to go through the steps that we used to do this particular experiment. So the first step that we'll talk about is site selection. How do you pick out an area that you want to do this experiment in? After that, we'll show you how to set up the actual plot, the length of it, and the head wall configuration. We'll then show you some of the pre-measurements that we do, and then we'll talk about the actual experiment where we set up the flow meters and velocity equipment, and then we start the experiment, and then we'll finish up back of what we do with the samples after we collect them back at the laboratory and back at the office. So the next part that we have to think about is how do you pick the sites that you're going to do this experiment? So you have to think about the type of treatments that you're interested in comparing. So on this particular site, we're comparing a skid trail that we had that had been compacted heavily during the salvage logging operation, and then we're going to compare that to an area that had been ripped or subsoiled with this wing blade behind a bulldozer to break up that soil compaction. So doing that, you have to think about, well, does this particular site look typical for the treatment that I had an interest in? Let's say if I was doing something with a mulch treatment, is the cover of that mulch about what I saw throughout the area that I'm interested in? So in this case, we looked at a lot of the different skid trails and said, yeah, this is a typical looking skid trail. And then we set it up so we had 6 repetitions of that treatment. We've learned that you need at least 6 to be able to do some decent analysis on it to account for the variability that you're going to see when you start doing these types of experiments. So this particular case, we have 6 plots that were compacted by the skidder, and then we have 6 plots that are paired, that are right next to the other one that had been ripped by the subsoil wing device that's being pulled behind a bulldozer. So I'm going to start walking you through the steps to get things installed. To get the soil moisture, have that in there. Good.
One other important task that you should do before the experiment begins is to get a sampling of how much cover is above any mineral soil that's been exposed. One of the important trends over time is how well vegetation is actually recovering in a burned area and how much mineral soil is still exposed. To do that with our group, we use a cover frame grid and a tablet that has an app that allows me to enter in the different codes for each type of cover that we might see. So the technique we use is a 1 square meter grid, and we have these PVC pipe cutouts that are labeled every 10 centimeters. So we sample 100 times total for each meter that we're looking at, normally about 2 meters per plot.
We are doing real experiments here, and I'm measuring soil water repellency. Here are my equipments: water droplet, ruler, datasheet, and stopwatch. Why we are measuring water repellency? Because forest fire affects soil water repellency, and it's increased, and this also affects infiltration. Because of we want to know how much fire affects soil repellency or not. We measure water repellency in 3 depth. First one is 0 centimeters, second one is 1 centimeters, and third one is 3 centimeters. We put 8 drops per each depth, and we time it how long it takes to infiltrate for each drop.
So using this large disc infiltrometer, we can measure the infiltration rate of the soil. That way we can know how much water is actually going into the ground during our Rill experiment versus how much is running off at the bottom.
With sampling for soil bulk density, we use 2 separate depths at 0 to 5 centimeters, so the surface to 5 centimeters down, and then 5 to 10 centimeters below the surface. The basic method is this is a slide hammer. We use this, pound it into the ground, straight down, and this cylinder on the top, when it's pounded into the ground, allows us, once it's in the soil surface, we dig down and we can remove it, and within this there's a top core that we remove, and the bottom core right here we can pull out, and the soil is within this, and this is a known volume. So with that, once the soil back in the lab is dried and weighed, we can back calculate and find the density of the soil, which allows us to measure just how compacted soils are. So we can then compare burned soils to, say, soils that have been driven over by a feller buncher or a skidder, and compare the amount of traffic and see what level of compaction has occurred, which can help us then explain the level of infiltration and what level of macro pores may or may not be present and compacted.
So now that I've located a representative site condition for the treatment I'm interested in, we're going to lay out the length of this rill that we'll use for this experiment. In this case, it's going to be a 4-meter long rill, and we've put in pin flags at every meter so we know exactly how far down it is for that 4 meters for the different measurements we'll be taking. And down here at the bottom, we're going to have a collection device for the water that's going to be coming through. That water will be laden with the sediment, and we want to have time-bottled samples that we're going to use during the course of the experiment. So the next step will be to install that collection device. To do that, we use some of this silt fence material. It's a little bit thicker than landscape material. This is the same material that we use for our silt fences that we use for plot erosion measurements on the hillside, hill slopes. and it works pretty well. So I'm going to show you the technique that we're using to install this. So here I have my silt fence fabric. I folded it over, and I'm going to use 2 layers of it as I put that in to kind of make a tight seal against the soil surface, so all the runoff is going to come over that. So in this case, I have already have a little gully that's been formed from the water that's run down this particular location. So now I have to line this area with the silt fence fabric, so all the runoff will come down over the fabric. So, and then I'm going to anchor that fabric with these landscape stakes that we use to hold the fabric in place. So now I'm going to dive right into installing that. So I'll move some of the big rocks out of the way so I can see what the terrain looks like that I'm going to work in. I'm right here at my 4-meter mark. I'm going to smooth out this edge on this side so that the fabric has an easier place to go as it goes up the hill. Okay, so I've got kind of a surface. Then I'm going to now start to attach this fabric. So I'll use a hammer to drive in the stakes. I'll start right in the middle and work my way out. So I'm working my way up, banging in the staples just part way to hold that fabric tight against the soil surface. And this particular site is pretty rocky, so a little bit of a challenge to get these in, and we'll see how well we do as we work through it on both sides. Okay, I've driven many of the stakes in, and they went in pretty well in the rocky soil, but I have some that didn't go in at all. So I'm going to try these spots again, and I'm going to change the angle that I was driving before. So I'm going to put them this way and see if that makes it easier for me to get these stakes in. You notice the hammer I'm using, it's a 3-pound or 1.5 kilogram hammer, and that works pretty well to be able to drive it in. So there I made that one in further than the other one by changing the angle. I'll try that over here as well. So now I installed all of the stakes, and we have a few that are still sticking out where we hit rocks. I put some at a different angle, but overall we have a pretty tight seal with the fabric and the soil surface. So now we'll look underneath, and here I'm going to clean this out and then install a piece of metal, metal that we bent to be able to use that as a collection device for the water coming off of the fabric into this. So I'll clean this out. So now I have my piece of metal. I've laid it in here, and I'm going to drive it as best I can into the soil to give a tight seal. So next I'll take some loose soil and fill in here on the sides. This helps stabilize the metal and tries to keep the leaking to a minimum. So now we've got this fence, this piece of metal pretty well stabilized with this extra soil in there. Then this last piece I can just slide underneath it and gently push that in so I can have a little bit longer trough to take samples at. One of the key components for this experiment is you need a water supply. So we have a water tender tanker truck here. This holds 3,000 gallons or about 10,000 liters. We can pump from any source like a river or a lake, and then we put that through a filter. And the filter that we use is right over here. Our large capacity filter filters the water down to 6 microns with a couple of filter screens inside. And then everything's connected with hoses down to our plots. Okay, the water will come to the top of the plot, and we put it through a flow meter, so we regulate the amount of flow that's going to go down the plot. Water comes in here through another filter, then into our flow control device, This here we can set to be different flow rates. For this particular experiment, we're using 12, 24, 36, and 48 liters per minute, and we run it at those different flow rates for 15 minutes. We have an electronic flow device here to tell us that how well this is working, so we can adjust the knob to get it to be exactly at, let's say, 12 liters per minute. The water then goes out the hose and comes into this device, which is like an energy dissipator. And this is just a metal can filled with styrofoam peanuts to spread the flow out so it's not in a narrow like hose. And it works pretty well. These flow rates are chosen based on different contributing areas that we think would be forming that rill flow, that concentrated flow. And we'll use the same flow rates for all the plots that we're doing on this particular study.
One of the other measurements we take is rill width and depth. For the depth, we use these nice WEP rulers. For the width, any tape measure with millimeters will work. We take these measurements at the 1 meter and the 3 meter mark once per flow.
Runoff velocity is measured using a salt concentration and conductivity probes. Two probes are used. One is located at 1 meter and the other at 3 meters down the length of the plot. A salt dye concentration is added to the runoff at the very top of the plot. The time it takes for this salt concentration to go by two conductivity probes is used to determine the velocity. A computer program is used to assist in this process.
During the real simulation, we take water samples. We take 6 samples each flow, and we measure the time to take each sample. Back in the lab, we process those samples to measure the volume taken and also to calculate the sediment, the weight of sediment in each sample. Because we know the flow into the rill and we know the flow out of the rill by taking all the sample at the end point, we can calculate the flow and also the sediment loading for each treatment.
We talked about velocity, we talked about taking samples, we had videos of taking samples, and we have to know what the timing of the samples are. So we have several timers set up, when to start flow rates, when to stop flow rates. We have an app on a phone to sample the time when you're actually taking samples. We've tried lots of different sampling devices. We've moved up to a phone this time, just using an app, and seems to be working pretty well.
So we've shown you some of the different parts of this rill experiment that we do in the field. This experiment has evolved over the years when we first started to what we do today, with just refining the techniques to make it more efficient Right now we're able to do 2 rills simultaneously to cut down the amount of time it takes to collect this data. So the other thing to think about is, what do we do with this data when we get back to the lab? So all the samples are collected, brought back to the lab, put into a drying oven, weighed, so we can determine the volume of the water that came down as well as the sediment concentration. After the samples are processed, everything's entered into a spreadsheet. We do a quality QA/QC check on everything. Several people will look at that data, make sure everything looks correct. The velocity data is then analyzed to calculate the velocities for the different flows from that 1 meter to that 3 meter mark. We take the width and depth measurements that were made, calculate the cross-sectional area of that rill at those locations to get the discharge. So we use all of this information to calculate the rill erodibility, and we do that first with the shear stress model, and then second we can do that with the stream power model. And we'll use those calculations to get the parameters that we need for physical-based erosion models, such as the WEP model. So this experiment's a great way to get to those parameters that you need to run that model in these type of conditions. Now, the other thing to remember is that you can use this experiment in a variety of settings. It doesn't have to be in a forest setting. It can be in a rangeland setting. You could be comparing treatment A to a treatment B. It could be an agricultural setting, comparing different cropping systems or different terrace systems in a cropping rotation. So it has a lot of options that you can modify and use this experiment. Now, one thing to remember is, why did we put so much effort into the rill erodibility component rather than the inter-rill erodibility? So if you're measuring inter-rill erodibility, you do that with the 1 meter by 1 meter rainfall simulator. And what we found is that in the steeper forest slopes, or steeper slopes in general, that concentrated flow is the most important piece. So this experiment is designed specifically to get at that concentrated flow to be able to understand the actual erosion mechanics of detaching that soil and transporting it off the hill slope. Well, I hope this video has been useful to you to learn how to do this experiment. If you have questions about it, you can write to me, Pete Robichaud, at Rocky Mountain Research Station in Moscow, Idaho, and be happy to discuss some of the ins and outs of this particular experiment. We've been doing it now for over 15 years, and it's been one of my most favorite experiments I do, measuring soil erosion. Thanks for watching.